Hi everybody. Today we're going to talk about Faraday Law, and this is a really good subject for the exam. Why so? Because Faraday Law actually summarizes many topics that you need. For example, how to find magnetic fields, and we talked about that. You have Ampere and you have Biot-Savart, and we're going to today talk a little bit about Biot-Savart. It's also talking about Lorentz Force. We're going to see that the Lorentz Force playing part here, and also about circuits. Remember circuits? So it's actually touching all these fields. To understand Faraday, you should have some understanding in each one of these components, okay? So examiners love this topic, okay? One question, boom, tack, a lot of subjects, okay? So this chapter also gonna be kind of a summary about magnetic and stuff like that. So let's not waste time. I'm going to this board and start. So what we actually gonna talk about today is system. I brought a ring, okay? Ring with current. So let's draw this ring. Put it here. Let's draw this ring. So what is the direction of the magnetic field? The direction of the magnetic field by the ring, by the huge ring. Okay, let's call it the huge ring. So we have here ring. Okay, so again, a recap. We have a ring with the current. In our situation, the current go in which direction? Anti-clockwise, right? Could be that way, which is clockwise, and it's go anti-clockwise. So field by the huge ring with, I'm writing it, it's a given, with anti-clockwise current direction, right? So we're trying to find what is this body, what is direction. So let me clear this one, and I want to do a summary because I told you that this subject, it's really good for a summary. So I want to do a table, and we're going to fill the table. So we talked about that if we want to find, for example, what is the direction? Direction. Intuition. Direction intuition. What we did to find DE, what we had the rule about charge, right? We know that if we have some positive charge, it's gonna repel electric field, right? And if we're gonna have some minus charge, it's actually gonna suck in electric field, right? Remember that? And what do we have in magnetic? If I want to find small direction of the magnetic field, we actually had the tangent rule, remember? So what actually make a magnetic field is a changing charge, not just a charge, changing or moving charge, right? So this Q, if it is moving, I'm gonna have some magnetic field, okay? And in general, how I can write a changing charge? It's a current, right? Current is actually, this is the definition. So how goes the right-hand rule? The right-hand rule, the first one, is actually saying this. Is asking you what? That the thumb gonna show you where to put the current, and the finger is gonna curl and show you where is the magnetic field. So if we're gonna go back to our ring, let me draw the ring a little bit narrow so you can actually see it 3D. So I'm gonna do it a little bit flatter, like this, right? And this is our axis. So if I'm gonna have a current in that direction, and the magnetic field is gonna be in red, so what I need to do, take my right hand, follow the wire, and the finger is gonna tell me what is the magnetic field. So I see that the magnetic field is curling around this thing, right? Curling around this thing and going out. Curling around this thing and going out. Curling around this thing, going out, and it's curling, right? So it's in this direction. So the magnetic fields around the ring are gonna be like this. I have this demonstration. So if I take in this ring, I need to follow the current. And when I do it, I see that, oh, the magnetic field is actually going in that direction. Aha, point where? In the Z direction. Here, pointing at the Z direction. And you see that they all accumulate here. Here, there's a really strong magnetic field because they all sign to the direction. Really, really good. But today, I actually want to find not only the direction, but also what is the magnitude. So let me clean this. So my question to you is, what is the magnitude of this magnetic field? How we can find it? Okay, so before I find the intuition for the direction, but I want also to know what is the magnitude, not only the direction. So what is the magnitude of B? Let's go back to our table, okay? This summary table. How did we find a small contribution? Small contribution of the field. Remember what we had? We had Coulomb's law, right? We had K, right? We had dq, this one, right? dq. We also have the distance, what? Squared, right? And the direction, which is the vector, right? This was the E, right? So we're gonna have the same thing for the magnetic. Okay, we have the same idea, but what's gonna change? This is not the constant that is anymore applied to us because this is electric one. So in magnetic, we have the permeability, which is this one, 4 pi. And if you remember, this term is actually, can get this configuration, 1/4 pi, right? It's the same thing. So this is this term, okay? Regarding the dq, what we have in magnetic fields, not a charge, but a changing charge. So we want here to have something that actually changed. So this is actually the current, right? Current is a changing charge, okay? And I need also to put the A. If you remember in Lorentz law, that we actually drive from this thing with the velocity to that idea. Remember this? So we have this, which is a moving charge on the location DL, right? And now I need to deal with that thing, right? This one. What is the distance? So it's the same concept. It's gonna be some distance. I call it RdB. I'm gonna explain to you later why. RdB squared. But right now here, cross RdB direction. So this is this and this. Do you see the comparison, how it's a parallel? And this idea is called Biot-Savart. So this is Biot-Savart. Got it? So let's try to use this thing to solve what is the magnitude, okay? So let's learn how to deal with it, how to use it, okay? So it's right that we have the ring, but we actually want to focus on just one piece of it, right? This thing. This is in a length dl, right? Have a length dl. It's produced magnetic fields, right? So let's write the equation. So dB, a small contribution, this contribution of this wire over here, this one, equal to what? Is equal to a constant. There's nothing actually to say about it too much. This one, permeability, is actually telling what material do I use, okay? So it's coming here. So here the magnetic field is in the vacuum. So usually that's what you're gonna have. And perfect. And I also have a current, which is given, right? The current is given. And then I got DL, okay? DL. So what is my DL vector? DL vector, you see here, is a vector that's going with the current, okay? And I need to give it a size. So if this is a ring, what the size can I give it to? With the radius R, and this is a small changing in the angle, right? D theta, right? So I can put here, right, D theta, and this is a vector. What is the direction? Tangentially, right? Going in this direction. So I need to give it this thing. And this is the hard thing about Biot-Savart. Just to understand what is the L. I don't say it's hard, but this is the hard thing in Biot-Savart. Find this. The second player, we have two players. I'm going back to this board. We have two players we need to understand to solve Biot-Savart. We need to understand what is the L, and we need to find what is this vector, the distance vector. So the distance vector is really simple. I put here mu f, mu0, 4 pi. Here, I need now to put RdB magnitude squared. So RdB is a vector which stand on DL, Here is, I'm standing on DL, and I'm looking at the point of interest, where I want to go, where I want to find the magnetic fields. Okay, so let's write it here. RdB is the vector which starts from DL on the wire, and go all the way to what? To B, question mark, to point of interest. Point of interest. Do you follow? That's all. If you find these two, Biot-Savart, easy question, you know the magnetic field, easy. So in our case, what is this distance? This is a ring, right? With the given radius. So this distance is actually the radius, right? So here I'm gonna put R squared. This is right the distance. So we know RdB in our case is equal to R. But what is the direction of RdB? Direction is what? Minus the radial, exactly, good. Minus the radial, okay? The radial is actually pointing outward, but we want to go inside. We are interested in the center, right? Perfect. So here I'm gonna do cross, right? Cross RdB hat. In our case, it's minus R, right? Agreed? Understood? And what we actually want, we want this small chunk of contribution, or we want to go all the way of all the ring, what's going on here? Because every one of them is a problematic guy that want to give his magnetic fields, right? So we want to contribute all to do the superposition. So we actually end up with B center is equal to what? To the superposition of, let's take out all the constant, mu0, I, 4 pi, and I want you to see that this one cancels with this one, you see? So we have here outside R, and we have integral that run on what? What is the integral running on? Theta. So we're gonna start at angle 0, and we're gonna finish one round, 2 pi. Perfect. So I have here d theta, perfect, d theta. And also, what is the direction of the magnetic field? We need to do this cross, right? That's gonna let us know. But we already have the intuition. We know what it should be. So let's do the cycle cross. So we have R, theta, and Z, right? And I know that this is the direction of the positive, but I need to start with theta. I need to do theta, cross R, and then only get Z. So because I go in the wrong direction, it's minus Z. But wait, we also have this minus, right? Wrong direction and a minus that was there from the beginning. So we end up in what direction? The positive one, right? So if you're gonna sum this up, we're gonna end up with B center equal to mu naught I for, let me shrink that a little bit. Center, okay? Mu 0 I 4 pi r and 2 pi, which means this pi and this 2 is dying out. And also this pi, right? So this is what I got. Let me check if we are okay. Everything. Yes, this is what I got. And in what direction? Z positive, right? And this is makes sense to us. Remember that we drew the lines, so we found it. So what I want you to take from this specific section, and this section I want you to understand. When you're working with Biot-Savart, you need to understand two things. What is DL? How are we going to divide my wire? In which way? If it was a circle, I'll be theta, of course. If it would be something else, dx, dy, dr, whatever you want, okay? And also the wire can be, I don't know, from many directions, right? Can be that way, that way, that way. Cut the wire, give many DLs, okay? As much as you want. RDB is really simple. You just need to keep this in mind, okay? I'm starting the other bolt. You need to keep this in mind. I'm starting at the wire and I'm going all the way to the point of interest. That's gonna let you know the size and the direction, okay? Got it? This table is really important. Let's move on to the next question. In the next question, I did something really weird, and you're gonna understand why I did it. I took this ring, you see it? And I decided to take this flame and put it in the middle, okay? I want to do it. You're gonna understand soon why. Okay, there's a crazy magnetic field, and I want to put this flame. This flame has a size, right? This one is A, and this one is A. Got it? A on A. And I'm gonna ask you, what is the flux, magnetic flux from this flame? What do I mean by saying magnetic flux? So let me clean the table, we don't need it anymore. So what is the magnetic flux? Do you remember what is, we are in C right now, right? See, what is phi b, question mark, of the frame? Frame, which is A on A, okay? So flux is really simple. Flux is taking into account also the field and also the area. That's all what is said. For example, remember that we have phi E, right? Which was the what? The electric flux. And it was equal to what? To summation of a lot of small fluxes of phi E. And a small flux is actually the electric field dot unit of area from this piece, right? So this was the electric flux. What's gonna be the magnetic flux? Gonna be the same thing. Phi B equal to a lot of small contribution of B, right? Which is gonna be equal to B dot dA, okay? But we need to decide on what area we are doing that. Remember, if it was a closed area here, it would give us Gauss's law, right? I didn't say it's Gauss's law. I didn't say anything. You said, I want to find the flux. Here I said, let's do the flux on an open area, on this flame, right? A on A. So let's do it. And if I'm going to tell you that this thing is really tiny compared to this huge ring, right? What this can give me, what information? Let's go here. I'm going to this part, the ball. So let's draw this here. Shh. Yogi, מה קרה? Everything is okay. My dog started barking. Maybe I feel that this is gonna be a hard section, so it's afraid a little bit, but no worries. Okay? So we have here this frame, and I'm telling you that A is much smaller than R. So let's do this. Phi B, the flux, equal to the integral of B dot dA. Okay? And what is the direction of dA? In the Z direction, right? What is the direction of B in the center? Also. So we can actually forget about the dot, right? B center and dA. We don't care about the dot, they're both pointing in the direction. Okay? But this B is changing, right? Here is different, here is different, here is different. But here in the center, it's B center, right? That's what we found. But if my A is so small, there's no big difference between this part and this part, and this part and this part, and this part and this part. They're pretty much the same. So the assumption that A, the size of the frame, is much smaller than the radius, actually telling you that B in this area is pretty much the same. You got me? You getting me? So I can pull it out, and we already found it. What was the B center? Somebody can read it to me? Mu zero, I, but what I, this I, right? Let's call it IR, which means the eye of the ring, okay? IR, what?
2R.
2R, perfect. And now we have to find what is the area of the frame, which we kind of know, it's a given, right? It's A multiplied by A. So phi B from Friends, right? Phi B actually equal to what? To mu zero, I of the ring, 2R multiplied by A squared. We found the flux. Perfect. Okay? So we understand the concept of the flux. Suddenly, in our equation, something really weird starts to happen. Suddenly, the frame, somebody take the frame and start to turn it, okay? If this is the frame, inside the ring, somebody starts to rotate the ring, okay? In what velocity? In omega, let's say it. Suddenly, let's write it there. Suddenly, the frame starts to turn around. The frame starts to turn around its axis, around its axis. Let's give us the velocity, how fast we're doing that. So theta, the angle of the frame, is actually equal to omega multiplied by theta. Okay? This is how it's changing. Good? So start to move. What would happen to the frame? Okay? And this is taking us to a really special occasion. You know, who are the big people in physics? Let's go to this word. Who are the big people in physics? Einstein, right? The 19th century. That's it. Einstein, love it. Who else?
Maxwell.
Maxwell, yes, but he's not the biggest like Einstein. There was somebody bigger than Maxwell. Who is it? Newton, like it. Newton. But what's going on here in the middle? You know, everybody always remembers the end at the beginning. But who was the great person here? You want to know who? What's the name of the class? Faraday, exactly. Faraday was a genius. Faraday noticed something crazy. Remember that we talked about that if we have a voltage, it produces what? A current, right? I put here a potential. Charge would like to go to some direction, right? We give them energy. And what we learn about the right-hand rule? What is making? It's making a magnetic field. And then Faraday asked really interesting question. He asked, dude, if I have a magnet, can I produce a current which gonna produce a voltage, the EMF? Can I make electricity? That's what it asked. And many people tried to do it, and they didn't succeed. But Faraday noticed something really interesting. He took this circuit. You have this one with some solenoid here. Here he put a voltage, and here he puts another solenoid, and here he puts some device that measures the current, the amperes. And he connected, and he didn't see anything. He see that this one is staying here in the middle, no current, because what he wanted to do, if there's a current, there's magnetic field right here, looking like this. So he said, I'm gonna put a magnetic field on this solenoid. And this solenoid, see magnetic field, will make a current and will give me a voltage. That's what he wanted to do. He wanted to do this. But nothing happened. He said, oh, this is a crap, this is shit. And turn off the battery. When he turned off the battery, he saw suddenly a spike. He said, there is a voltage. And then he go back. He said, wait a minute. And then he turned the battery on. And then he saw another spike. And then he understands something. If I have things that change in time, I do have this phenomenon. Okay? Let me give you an example. Take me to the demonstration. So here, like the frame that we have, the same thing like the frame. See, I have an area, I have a frame, right? And I'm taking a magnetic field. This is magnetic field. Look here. Let's do that. Look here. Nothing happened. Nothing happened. But if I'm gonna change stuff in time, for example, I'm gonna take the magnet and put it inside, only when things change. If I'm gonna do it slowly, nothing changed, nothing changed, nothing changed. Now let's change time fast. Hop! You see what's happened? I actually have some current. And another example, let's do this. If I'm gonna take this famous experiment, I'm gonna change magnets and I have electricity. So actually we all owe a lot of money to Faraday, because Faraday actually start economy of electricity happened. Do you understand this concept? So let's put into equation what Faraday actually understands. So Faraday saw this stuff, okay? Faraday saw this equation. If I want to produce a voltage which called EMF, electromotive force, with unit of voltage, let's do a square. What I need to do, I need a changing in time of the flux of the magnetic field. Phoebe from Friends. If she's going crazy in time, we have a voltage, okay? And I want you to notice that here we have a minus sign, okay? We have a minus. From energy reason, we're gonna talk it in the last section of the tutorial, okay? We're gonna discuss about this minus. So what can actually change in time? How can I change this Phoebe in time? What can I do? Let's remind you, this is actually integral of B vector dot dA vector, right? I'm running on some area, right? So if I already reviewed. What I can do to change the flux? First of all, I can change what? If I changing the magnetic field, right? I actually changing the flux. This is gonna change, this is gonna change, this is gonna change. Okay? So first is this. First is this. Also, I can change what? The size of my frame, of where I'm gonna check the flux, right? So this also can change in time, right? What else can I change? What else? We miss something. Huh? Current, but it's related to B, right? Remember that we write B. Where's the equation for B? You had there the current. So you can change the current, but changing B. You can change the distance, but it's changing B. It's the same concept, okay? So we can change what? The direction between them. Okay? If the magnetic field pointing that way and then suddenly to that way, something is changing, right? So the last term is actually, not to forget that V dA cosines theta in time. You see it? You understand? So that's exactly what we have. Somebody changed, and if you go to YouTube, I actually give you one question about that and one question about that. So now we do the last one of these, you know, options of the examiners. Yogi, go. Just a second. His name is Yogi.
Yogi.
Yeah, Yogi.
That's my dog's name.
What?
That's my dog's name. Yogi.
Your dog's name?
Yeah.
Ah, nice. So they are twin brothers. Okay. So perfect. So we got this thing down. And so let's write what's going to happen. I'm going to this board. Okay. So what's going to happen in the frame? So I'm answering this question. So first of all, we have a changing angle, right? This is going to change, right? It's going to start here, then go there, then go there, then go there. There is like changing theta, right? Of the frame. The frame, this position, and this position, this position. So the angle of the dot product going to change. Which what's going to happen? It's going to make the flux to change, right? The flux is going to change in time. Which what's going to happen? Make an EMF, right? Going to make an EMF, a voltage drop on the frame. And what a voltage drop do? What it do to charge? Move it, right? And what we can do with current? Turn on the lights, loudspeaker, do whatever we want, enjoy the car, whatever you want. You produce energy, okay? So this is what's going to happen. So we found this thing. Sorry, we didn't found this. We found this when the angle was constant, right? We want to find this as a function of time. So let's update our solution. So let's find what is the EMF. Let's find the EMF. So we, Newton, Einstein, and Faraday, I love you all, but I need a space on the board. Perfect. So we want to find epsilon, which is equal to minus dt of phi b. And we know that phi b was equal to what? Minus d time, right? Equal to, we found it, mu0 I squared of what? Of the ring, 2r. And notice that I put here off the ring because we're going to have another current, right? It's coming up. So I want you to notice it's not the same. I squared. And now we need to correct what we have, right? Because we have the dot product, remember that we take off the cosines? We cannot do it. We should put here cosines omega t, right? Which this is theta, right? We cannot neglect it. So if you're gonna derivative this in time, they actually only term the change in time as cosines, right? So this end up to be plus mu0 IR squared 2r omega, right, from here, and sinus omega t. And because it's a cosine, it gave me the plus. Got it? So we found the EMF. Nice. This is the voltage that we had. So, and I want you to notice that this cosines, right? So it's actually what it say. Take me here. When the frame is like this, the flux is what? Max. It's really strong. But when the frame is in this orientation, right? There's no flux at all. But I don't care if there is a flux or there is not flux. I care that the flux is changing. If the flux is changing, I'm gonna have energy. Got it? Nice. Okay. So another question that I wanna ask you is what is the current that we're gonna see on the frame? on the frame, there's going to be a current. So in order to know what is the current of the frame, I'm going back to there. In order to know what's the current, you need to know also what the resistance of this flame. So I'm going to give it to you. I'm going to say the resistance, the flame has a resistance of lambda, okay? Lambda, which is omega per, sorry, the frame has a resistance per length, which is a really nice way to measure resistance. You have a big stuff, you know the material, you check from here the current and the voltage, and you know what is the resistance per length. So, okay, this is a new quantity. It's just omega divided by meter. If I want to know the resistance, what I need to do to get rid of this one. So I need to multiply by the length. Got it? So just a reminder, resistance, I do double line here because we have the radius also. Not to confuse. So is by 8, right? That's all. Okay, remind resistance. And this term is actually this. And this is length. Good. Okay, the frame has a resistance per length of this. What is the current? The current of the flame. So what we can do, how we can find the current? We have the resistance. And we have the voltage, so which law? Ohm's law, or how I like to say the Beer law, okay? So I'm gonna clean this one up. So I'm going back to this board, thank you. So we know that Beer, which I like to call Beer, will hold. So we want to find IF, which is the core current in the frame, through the frame. And we know that the resistance is, this is the resistance, is just lambda multiplied by what? The length of the frame. So the length of the frame is a square, and each one is A. So we have 4 of those, 4A, right? Divided by this thing, right? The voltage. EMF. Oh, you're right. Sorry, the other way around. Divided by R. So sorry. So we have here the EMF, which is this, divided by the resistance, which is lambda multiplied by 4A. Okay? So this ends up to be mu 0 IR squared omega 8 RA, right? 8 RA sinus. So what's happened to the current is actually what? Is going on the frame. This is the frame. So the current actually going in the direction and then change the direction, right? Is always changing. That's what you have here. Because the flux is also changing, okay? Sometimes the flux is grow, sometimes the flux get to the minus, right? Okay. So this is the current of the frame. Cool. So my question to you is what the direction of the current, okay? What at the beginning, okay? At the beginning, it's gonna be anti-clockwise or clockwise. What's gonna happen? And this take us to a really nice concept that's gonna give you a lot of intuition. So what is the direction? Let's do the problem again. This is the ring, right? IR. Going in the direction. We have here in the middle the frame, A on A, right? And it starts, it's want to rotate, right? Want to rotate around its axis, around this one. What is the direction of the current? Okay, so IR is anti-clockwise, right? So the way to understand this is to understand the idea of conservation of energy. The current will try to stop the change. I repeat because this is super important. The current always will try to stop the change, like friction. If I have a box and I want to push the box, okay, I'm pushing really hard, pushing the box. Where's the friction direction? If I'm pushing that way, the friction will try to stop the change, or try to stop me. If I go from the other side to the box and try to push it from that direction, where's the friction goes? Opposite, but it's the same friction. But the friction is always opposed the motion. The current in the frame always oppose the change, like the friction. Understand this concept? Okay, so how can I stop the change? Look, if I have here, I drew it a little bit bigger. It's not to scale, just for you to understand. We don't need a ring. We don't need a ring. So at the beginning, what is the angle between V and the area, dA? 0, which means I have a lot of flux, right? I have a lot of flux. Every V is pointing in the direction. I have a wonderful area, a good real estate, you know, to invest, a huge area, okay? But then what's happened? Then I start to tilt, right? With some theta. In some omega, sorry. This is the rate.
Given that it goes up,
Huh?
given that it's like that.
It's continuous, continue turning around. It can be a few cycles. It's okay. No worries about that. Okay. It's gonna end up, for example, that really this direction, and here what's gonna be the flux? 0. Here's the flux is 0, and here the flux is max, right? So this flux is actually what is dying out. You see it? So what the current will try to say and do, say, flux, don't die. I will help you. I will try to make you survive. That's the idea. So the current, using the right hand rule, okay, will try to give it a push. I need to strengthen the flux. He's dying out, okay? He's choking. Somebody start to turn around. So the flux will try to produce what? A magnetic field that's gonna feed this flux that's dying out. How we can do it? Right hand rule. So this is the direction of the current. You see it? Understand? And what's gonna happen after this moment? After this moment, the flux, after this moment, it's gonna tilt to that way, right? And then it's gonna gain area. So the current say, oh my God, you become stronger in time. I need to stop you. And then the current will go the other direction to stop it, okay? So it's like friction. It stopped the motion. So if the ring was in that direction, right? The current was in this direction, anti-clockwise. So the current again would be anti-clockwise. And I want you to understand that like in physics 1 that we talked about friction, we also have a real force that tries to stop us. And this is what? This is Lorentz Force. Think about it. You have a frame, you have a wire with the current in a magnetic field. This is Lorentz, right? So you actually have the force that being generated to stop the motion. And this is how you produce energy, okay? Think about it, that if I'm gonna push the box and the friction would help me, so I would accelerate the box, and friction would push it also. So nothing would stop it. It will continue to infinity, right? It's accelerating more and more momentum. So the same concept here. So the current would stop you to produce more and more energy. We'll try to stop you, okay? Let's write what is actually the force. Let's do it. I think we have a few minutes. I think it's a good thing to do. So what is actually the force that's gonna be on the frame? So what is Lorentz force? Remember the equation? What is Lorentz? on a wire, not on a particle, is I integral, right? dl cross b, right? And which I is this? The I of the not the ring, the frame. The frame is actually the one that's been trying to be stuck, right? So this is I frame, right? But I can simplify this, not do the crossing stuff, and I know it's a square, so I can write actually IF changing in time, right? BL. L is the length, right? What is the length of, for example, this one? Only this. This is A, right? A, this is the length. Let's do this. Length. This is A. We found it, right? What was it? It was mu 0 IR divided by 2R, right? And we found this. This was mu 0 IR A omega 8R lambda sinus omega t. Okay? So what's going to happen? So the frame will get to this position, and the force will try what? To change the direction. It's going to be applied here, and here it's going to be on that side. Okay? Just take me to the board. I'm going to just do it briefly because we're short in time. What I want to say that you actually have a force that's trying to stop you. In this specific situation, you see that the force actually cancel each other, but don't worry about that. But you also have moments, right? About this. So there's force or moment. For me, it's the same. Okay. Moment is a force that tries to turn you around. So the force actually cancel, which means the frame will not accelerate its location to other location, to other place, but it will do change because there's a moment here and a moment here to try to stop you from turning around. Okay. So this makes perfect sense. So that was the subject of Faraday, and you have two more questions on YouTube. If you saw it, good. If you didn't saw it, so go and see it. It's really, really good. One is about the magnetic field that they're going to change, and the other one going to be that they're going to change the area. Think that I can change the size of the flame, make it big or small, like a heart, moving flame I can do, or just extending in time. Extending. Or think about it, then what's happening? I have more area. I can change B. How can I change B? I can put more current inside, right? Do that the current is go linearly up. So the flux is always said, oh my God, I feel more magnetic field. Okay, like here. I feel suddenly somebody push a magnetic field, right? In this demonstration, right? Somebody push a magnetic field inside, right? So this thing is actually what makes our economy work. Also, another trick is I can put the magnetic field in place, but I can get close to the source or getting away, right? There's many ways to play. This is what I just said. I think they are the main ways to do it. And you have only three players, the angle, the magnetic, and the area. How you're going to change each one of them? Up to the examiner, how you want to do it. Good. The next subject we're going to talk going to be the last subject of magnetic. We're going to finish magnetic. The last one going to be inductors, which is L, which is the parallel thing to capacitor. Capacitor learn how to actually accumulate electric field, and inductors actually know how to accumulate magnetic fields. Okay, that's their job. Okay, so the way to store electric energy, and there is a way to store magnetic energy. And after that, we're going to finish the subject of magnetic fields. And as I told you before, always I want you inside your head to always think, go back to the table, always think about, okay, what is the parallel subject in electric fields? Because that's going to help you to remember and understand the concept, because they're working the same way. Okay, so glad to have you here today. It was a wonderful tutorial. And if somebody can help me with the demonstration, take it back, it will be wonderful. So see you guys. Cheers. See you next time. If you have question, go ahead.